So let's look at an example of a combustion equation, okay? In this particular combustion equation, we have carbon, elemental carbon, combining with oxygen to give or yield carbon dioxide. So you can see it's a combination or synthesis reaction, a special type called a combustion reaction, because the element or compound, in this case it's an element, is combining with oxygen to give us a new compound. Okay, so that's a combustion equation. Sometimes we call it burning carbon. Okay, when you burn something, oxygen is the reactant. That's combustion is a fancier word for burning. Okay, so carbon burns an oxygen to give carbon dioxide. All right, now you'll notice that this particular equation here is a model to describe what we see. If you take a pure sample of elemental carbon and combine it with oxygen, you're going to get just this one product, carbon dioxide. This is another way to model the same chemical change. In this way, we call this a space-filling model, where we have this one single sphere is representing the elemental carbon. These two spheres that are pushed together here in a covalent attraction is an diatomic element, two atoms combined as a molecule to give you the way oxygen exists in nature. And then this is the space-filling model of the carbon and the two oxygens chemically combined to give the molecule carbon dioxide. And you'll remember from the last lecture in your homework that this is a molecule. It's a covalent compound because it's a combination of non-metals. That's going to give us this special case where we call it a molecule. A covalent compound is another word for a molecule. All right, so we have different ways to model the combustion equation, and you should be familiar with both of these ways that we model it. Okay. Here's another example of a combustion equation. In this case, sulfur is the molecule that is combining with oxygen to give the compound sulfur dioxide. It's a molecule, sulfur dioxide. And again, you can see we can model it with letters and little numbers, or we can model it with these spheres that we call a space-filling model. They both tell us the same story. And as a chemist, when I look at this S, I think single atom of sulfur. When I look at this O2, I'm actually thinking two oxygen atoms chemically combined. And when I see this SO2, I'm actually thinking sulfur with two oxygens attached. Now, you may not be able to, at this point in your career, look at SO2 and know that the S is in the middle and the two oxygens are what we call terminal. We'll get to that in the next chapter. For now, I just want you to know that in a molecule of sulfur dioxide, you can read the name properly, sulfur dioxide. If I said sulfur dioxide, you could write SO2, and you could model it this way, or some way. It doesn't have to be exactly right at this point in the game, as long as you get one sphere for sulfur and two spheres for oxygen. Okay? So you can see it's balanced. Matter is conserved across the chain.